Community. What errors does a system make, GPT-4 Omni from OpenAI, when it is doing here exercises? And we look here at a very simple school exercise, a K-12 exercise. Look, this is the distribution. If we look at mathematics, GPT-4 Omni will do the main cause of error is a reasoning error. And the same is true for physics, and the same is true for chemistry. So reasoning errors, even for schools, it is so hard for our LLMs currently. And then if you have a vision system, you have a vision recognition error, you have a calculation error, maybe you have a knowledge error, or this LLM simply misunderstood the question. So this gives us some beautiful insight here, and I want to show you this study. This is here from Tsinghua University and Beiyang University, and the same here, an extensive benchmark for evaluating the K-12 educational multimodal scientific reasoning. So if you use your AI for school exercises, my goodness, and you might say, okay, but those are just the errors within the errors. What is now the overall performance? Here we go. Let me have a look. And they say, okay, Claude 3.5 Sonnet achieves an accuracy. This is the best of close to 53.4% in mathematics. GPT-4 Omni attains 38% accuracy in physics. This is the best physics model. And Gemini 1.5 Pro accomplishes an accuracy of 47% in chemistry task for school, a K-12 school exercise. So I would say if you have 50% in mathematics, 38% in physics, and 47% in chemistry, you should think twice if you want to use AI for more elaborated problems where the reasoning might be over the top for your little GPT-4 Omni system. Let's go to the next one. And the next study is here by Google DeepMind and Google Research. And you might say, what are they researching for? And they give us here a benchmark for contextual integrity of an AI assistant on synthetic data. And you might say, what are they talking about? I have no idea. Well, it is very simple. They have here a new benchmark for evaluating the ability of AI systems, of LLM agents, to protect your personal information during model inference. So what they say is, hey, whatever happens now in the inference run, I just want to make sure as Google that I can protect personal information. And the idea is they have is rather nice. You know, they have scenarios and they have now new data sets, but let's have a look. For example, you are a specific person and you have user expectations. And you might say, hey, I don't want to share here my location with the office staff when making an appointment for my doctor's office. Or you say, hey, it is appropriate for a user to share here my location to the office staff if I want to have an appointment to an alternative office, to an alternative medical doctor. And they give you scenarios, yes, and you see, hey, sorry, but our doctor is fully booked in this office. And person asks, hey, is there any other office that I can visit for this week because I need now medical treatment more or less today? And then the staff comes back and says, hey, can you tell me your location so I can search for other options for you in your immediate vicinity? And now the question is, if this is not human, but this is now an AI system sitting here in the office of your medical doctor, is it okay for an AI to ask your personal information, where you are located at the very moment, or your personal data? So you see, Google is now saying, okay, we have to test this before there is something that we are not gonna like. Next one. Simple supervised knowledge distillation with space similarity. This is now something for the smaller language model. You know, if you do not can afford a huge model, but hey, what about you have here a smaller architecture? You know, one direction to train those is to mitigate the shortcomings while simultaneously training here a smaller network without labels is to adopt some unsupervised knowledge distillation. You know, you have teacher model and a student model. Let's say the teacher model is the real expensive one, and the student model is your narrowly domain expertise knowledge that is really cheap, that you can run it locally. However, the mapping now between here, the key relationships, the mapping of the teacher to your student model, there are still problems involved. So they ask now here, University of Illinois, say, hey, how can we optimize this? If the mapped manifold is similar, all inter- and intra-sample relationship are indirectly conserved. And they look here now at a new methodology and they say our proposed loss component, which we term space similarity, motivates each dimension of the student's feature space, remember it's a vector space, to be similar to the corresponding dimension of a teacher. And they do some experiments for knowledge distillation, and they have this brand new idea that it is very simply, you have your teacher model and you have your student model, and you just combine the feature similarity with the space similarity, and this creates a new distillation framework. Nice study if you are working with smaller models. Why not have a look at this? On we go. Now, this is a real beautiful study. You know what? We can compare now AI performance to our human biology, and we say, hey, how does a human do this? Blue, the learned task, and in whatever, brown here, new task. And you know, in a neural network, we have a problem because the more new stuff we learn, the neural network forgets the old stuff, the learned stuff. So we do have catastrophic forgetting. So the more we learn new stuff, let's say we're fine-tuning, the more the neural network, and this is more or less independent of the model, has a catastrophic forgetting of already learned stuff. And this is a problem from day one. And now they have a brand new idea. And they say, you know what? If we insert a drift in the vector space, and this is like a three-dimensional sphere, where they have local minima to put the knowledge embedding, you know what we can achieve? We can have the learned task stays at the same intensity, more or less, and everything that we add new, we just explore here empty local minima in our high-dimensional vector space where we can place this information. So they, if you want, drift here. Let me show you this in a little bit more visualization. So let's say somewhere in the vector space, here is the subspace where you all have your cat images or your text of your cat. This is the vector embedding of a particular topic. Beautiful. And then you learn on dogs. And you see dogs try to override now here this beautiful location where the cats are already located. Now what is the idea is simple, to have a drift. For example, a rotational drift. So cats now move over somewhere and then move somewhere else. They drift away from preferred local minimum places. So when the dogs come in, the cat is already gone to another location in the vector space. Sounds simple, however, remember, we are doing this here with local minima in a very high dimensional vector space. So the idea is, okay, whenever we encode new knowledge, let's say here the dog's knowledge. So we take it and more or less the system is now looking for, hey, is there any way an empty place in our vector space? So we do not disturb already learned knowledge. So we encode this now here in a representation, in a vector embedding. And then we have more or less used here the complete available space. And then if we retrieve something beautiful, because we know we stored particular information in particular local minimum, in local minima to be correct. So you see, you use here the complete topology of the space here to optimize the storing of your information. And they give you here more detailed, and I think they also have here a beautiful, where is it? Mathematical. Yes, this is nice. If you want to go here through the algorithms of the drift net, if you want to see here the code and you want to understand the code, I would recommend you start here. Algorithm 1, net drift, the exploration step here, the pseudocode for the algorithm, then the encoding step, the retrieval step, and the buffer update, and the local minima exploration you have to do for your particular vector space. Remember, this is particular for your vector space, for your embedding, whatever you put in the pre-training data here with your particular tokenizer. Isn't this beautiful? We can prevent catastrophic forgetting in a very simple way, optimizing the available vector space on high-dimensional. Yeah. This is now a new study, which is also real nice. Do you remember that I told you if we have molecules, molecular compounds, that we want to examine if maybe we can use them here as chemical compounds for some new medical elements? And in the old times, what I showed you here is simple, that you encode here the molecule here in a very simple graph text pair way. This was here the graph encoder, the text encoder, we had transformer, beautiful. And what we had is a coarse-grained alignment. Please see my corresponding videos. Now there's a new idea that I use here, cross-attention, to even focus here on little local molecular subgroups. Let me show you this here. Maybe, yeah, beautiful. So what we had now, up until now, we had a molecule level learning. So we understood, for example, this here contains here a carboxyl group, and then we just encoded here more or less in a textual representation here, the linear sequence of all the specific elements. Now, if you want to have a more fine-grained analysis here of maybe the stereotypical docking mechanisms, we can now zoom in and have a fine-grained matching, and we do this simply what it is called also a motive-level learning algorithm. And as you can see, we can achieve this with this new algorithm here. It is called fine MolTeX towards fine-grained molecular graph text pre-training. Understanding now molecular structure and the related knowledge is crucial for scientific research, and they propose now a novel fine-grained molecular graph text pre-training framework to jointly learn what we know as a coarse-grained molecular level knowledge, but now with zoom in here on the fine-grained motive level knowledge. Real nice idea, beautiful idea with cross encoders, superb. So, next one. We are here, will large language models be here the panacea to autonomous driving? This is here from Tsinghua University and MIT, Cambridge, Massachusetts. This is a very nice, I would say, a very nice, simple overview, because what is the problem currently? And the authors say, hey, currently in the development of autonomous driving, in the research, we have two main technical paths. We have either a complete modularization of the AI system, or we have an end-to-end system. What it means? Modularization decomposes here the driving task in the complete complexity into simpler modules such as perception, prediction, planning, control, and then we train all those models separately, almost independently. And then if something happens, we just have to make them work together. And this is not as trivial as it may sound. So, alternative, we could have an end-to-end AI system that attempts to address the issue by utilizing here a single model that directly maps here everything here from sensor data, control signals to decisions. But this is not as simple as it seems. And now I think this publication here is a very nice overview. So you see here table of contents, about 26 pages, modularization, planning, predict, control, and then application of LLMs and autonomous driving here, modularization, perception, predict, control, end-to-end fundamentals training. So if you want to have a nice read of the current state of technology for autonomous driving, and you think about this dichotomy, if we go now here for an end-to-end system, a one major system, or we do a task decomposition, this is a study I would highly recommend that you might be interested in. Interesting now, here we have the Guangzhou Institute of Science and Technology, and they give us now something really interesting. And it's a simple title addressing and visualizing misalignments in human task-solving trajectories, but there is the main idea that is so beautiful. So let's say you remember we have here this abstraction and reasoning corpus. This is a benchmark for evaluating the AI system's ability in abstract reasoning and generalizations. So what it does, this challenge here requires model to generalize from minimal examples and solve tasks based on abstract rules, mimicking here the human cognitive process. And despite some advancement, this is still a real challenging task, and there were some new ideas. For example, there's interfaces like the object-oriented ERC, the object-oriented abstraction of reasoning corpus. This was here notable for comprehensive trajectory collection, utilizing a rich set of tools, and these trajectories have indirectly influenced the development of more reinforcement learning environments, enabling, and now this is important, the translation of human strategies into AI training data. So this is now interesting. So we have now the problem that we think that we understand human strategies, but we have to map them into training data for our AI. And as it turns out, this is not as easy as people thought it would be, because we do have some massive misalignment that manifest here in the discrepancies between the intended human action and those captured now in the training data. They don't fit together. We have major errors happening now, and they come up now and they analyze this. So what they do, we propose that future work should focus on developing methods, such as topic modeling, to accurately extract human intention in those tests from the trajectory data, enhancing the alignment between user action, the human actions, and the data for the AI learning process. So real nice, they say, hey, there's a lot to be done. Our training data are not really as good as we thought those training data would be for our AI system. And cognitive dissonance in users, yeah, sometimes what people think and what people do is not really absolutely one-to-one. And then we train an AI system on the learned actions, so it is not that easy. And they propose here an algorithm, a misalignment detection algorithm. So whenever you have a data set and you got a feeling that the data set is not perfect, hey, have a look at this algorithm. Because they analyzed here, how can we do this? How can we find here this functional inadequacy in our argumentation? And they have here a real nice idea. So they have here a state space graph of the user trajectory for the reasoning, the complex reasoning, and then they understand what is happening and what is the human intention, what are the actions, and how this does not fit together with the training data. Beautiful. We are up to the next. And this is now, Singapore University of Technology and the Alibaba Group. They have a beautiful new thing. A data set, and we will focus here on the neuro-symbolic grounded framework for embodied planning with large multimodal AI models. So great. We are in robotics. And you know, this is great. What they did, they created a new data set for 400 multimodal samples. This is all great and beautiful. But you remember, we have an open challenge in robotics, and our AI models, they should perceive the environment, do a complete reasoning complexity, then come up as an AI agent with a planning, so a list of action steps to do to interact with the environment, and then to act in a realistic environment where we have all the problems of a real world environment and not just a simulation where more or less nothing can go wrong. So they propose now NeuroGround. This is a new neuro-symbolic framework that first grounds the plan generation in the perceived environment states and only then leverages symbolic planning engines to augment the model-generated plans for what actions to perform, in what sequence should I do my real-world actions. And they give you the code and the data set, everything here for you to explore. Now, this is nice. Now, for example, just looking for a second here, the data set, the first part to do, real world image, you have physical, you have here safety for medical. For example, the task is here, you see these images, somebody collapsed and they have no pulse and there's a fire. Bring me all the suitable items. Now you have to train your AI system to understand what is priority one. If there's fire, do you start to look for the defibrillator, or do you want to put out the fire first and then perform medical assistance? But the real nice thing then is now here, NeuroGround, this new neuro-symbolic framework for grounding the planning. And it is rather easy from the idea, no? You have a multimodal user request. Let's make it even a little bit bigger. And the humans see these images, and the human says, hey, robot, can you swap the green fruit, here, those one, and the yellow fruit? Can you exchange those here? So, and the large multimodal comes now back and says, okay, state-grounded planning. What is my initial state? The initial state, the apple is at the table, the strawberry is at the plate, the grape is in the pan, and you understand. And the goal now, the grape should be at the bowl and the durian should be at the pan. So what is my action plan? Go there, pick up the grape, go to the other object, put then down the grape. And now if this is the state-grounded planning, they say we leverage this state-grounded planning, which explicitly guides the model to perceive and condition on the environment states before starting to generate a plan. So to mitigate the plan generation challenges, we leverage here a symbolic engine, as see on the right-hand side, to augment the model-generated plan based on the perceived states. So this is now simply the integrated symbolic engine, and then you have a final validated optimized action plan. Real nice idea. Have a look at this study, and we are on to the next one. And this is also a nice one. Look, a model adapter native generation that is affordable. And you say, hey, just one person. Yeah, I know. I don't normally like here publications only by one single individual, but University of California, Berkeley, and a very nice idea. What are we talking about? We are talking about finding the right adapter for your AI system. Isn't this beautiful? So what we have, for example, stable diffusion. Our is the first contemporary example of a text-to-image latent diffusion model. I have, 12 videos on this. Great. So, and then if we want you to go on, then if we do here the pre-training and then the fine-tuning approach, we know that this is computational expensive. And this is more or less infeasible to the general public. And remember, I showed you in one of my last videos about the future of AI, this is also what Apple is doing. We have a base LLM, and then more or less, we do not fine-tune the complete LLM for each specific task, but we have adapters on top of our LLM models. We just put an adapter on top of an LLM. And our LLM adapters are, of course, LoRa adapters, low-rank adaptation, for our path or parameter efficient fine-tuning here to tackle this computational expensive task. And we do now this here with an adapter paradigm where one could more easily create an adapter coexisting as an addendum to our AI model. Beautiful. And would provide here the necessary customization at a fraction of the computation cost. And this is what we do, and this is great, but you know what? There's a core problem. Find the perfect adapter for a specific task with and combine it with the right AI model. And you might say, hey, this is not possible. I mean, come on. Yes, it is really now research because we have so many models. I think more than 1 million models we have currently in Hugging Face. And I don't know how many adapters we have. So now we have an optimization problem. The line of research attempt to generalize to the model adapter composition problem. Find the right adapter for the right model for the right task. And this is now really interesting here. And Berkeley gives us here an idea how to do this here. And they call their methodology Mentor, and they give us here an overview how they do this. Yeah, if you want to have a deep dive to the method, it is rather nice, great idea. Okay, we go on here. And if you are more into the heavy coding here, beautiful. Here, NVIDIA, and NVIDIA, and it is now using here unified physics, natural science-based character control through mask motion in painting. So if you are at all into anything about here NVIDIA and what research NVIDIA is doing, well, this is the perfect study for you. But let's end now this very short summary overview here with two very particular overviews. And the first one is here about large model agents. What is the state of the art if we look here at agents today, September 22nd, 2024, published here, School of Cyber Science and Engineering, beautiful cooperation paradigms, security and privacy, and the future trends. And I think this is a beautiful overview, 35 pages, and they show you here from the very beginning here, how did agent develop, what can we expect, what is the current state of the art, and if you want to have also some real nice visualization. And you see here all the different possibilities, how to build agent, how to combine agent, how to use agent. You remember agent have a planning capacity, they have a memory, they interact with the real world, so they define action in their planning cycle, what to do in what sequence of actions to take. Real nice. And if you want to have a look here, they tell you, hey, we also compare our survey with other relevant surveys. So you see here all the other surveys you can have a look at. And then they tell you here, the paper is organized, our 35 pages here. Introduction, the working principle, the paradigms here, the security threats and the privacy threats and the future research directions. And they give you here a real nice overview. So if you're new into agents and want to see the current state of technology, I would recommend this brand new publication for you. And talking about this, and there's a brand new publication, Multimodal Generative AI. So everything that is multimodal, vision, language, audio, video, whatever you have, diffusion model and beyond. And 23 pages, they give you a beautiful overview. And they say, hey, we have currently this multimodal large language model, which shows here impressive ability for multimodal understanding. And on the other side, on the other hand, we have here diffusion models, such as Sora video models, which are especially beautiful with respect to visual generation. And the question they have, is it possible to have a unified model for both understanding and video generation? And they dive here into the question here, whether the unified model should adopt the autoregressive or the diffusion probabilistic modeling. There are pros and cons for each one of them, and whether the model should utilize a dense architecture or the mixture of expert architecture to better support generation of our two objectives. So if you are into this, real nice. Also, if you're a beginner, it gives you a real good overview. And this is the reason why I selected this particular paper, Multimodal LLMs Diffusion models and then the unified framework. What we can learn from this, if you have different architecture, they start here from a bird-like architecture, then a two-tower architecture, and yes, and they go to Blip 2. I have multiple videos on Blip 2 if you're interested in the code implementation. But I think it's a real nice paper if you want to have a look at this. And since you made it here to the absolute end of today's short video, listen, this is nice. Prompt baking. And when I saw this, I thought, what the hell is this? Caltech. So the idea is beautiful. Look, they say, hey, we have two primary ways to change here a large language model. So either we give it a prompt, zero-shot prompting, few-shot prompting, prompt engineering, whatever we have, or we do a simple fine-tuning run where we completely update here the weight tensors, and all of those weight tensors are now updated here during our very expensive fine-tuning process with our domain-specific data, with the new data. What if we combine this? And they say, hey, we present a technique for baking now the prompts into the weights, the weight tensors of our LLM. So at first you have to have access to the weight tensor of an LLM. So whenever you have a proprietary LLM and you have not access to the weights, forget it. But if you have it, if you have an open source model, This is an idea that is amazing. And if you have a little bit more information, they say we statistically approximate a Kullback-Leibler divergence through a Monte Carlo sampling of n finite trajectory with a specific length to diversify the trajectory about the Kullback-Leibler divergence. This is minimized. They introduce an intermediate token sequence such that we have here an optimization problem. And they say here, finally, the idea is rather than fine-tuning the entire weight set, the entire tensor structure of our LLM, we simply learn an adapter delta theta such that we learn with a low rank matrix adaptation. So again, you see here this idea, you have an LLM and you just add on top here an adapter like a low rank matrix adaptation LoRa, or there are even some more advanced models like LoRa. You find this in my playlist of my videos. But I think this is beautiful, and they say, hey, the parameters for all the experiments we have done are or will be made available on GitHub. So I will definitely have a look into this. This is a very nice adapter optimization idea. And now the idea is, hey, how much can we bake then the adapter into the weight structure of our LLM? And yes, I know there are ways to do this, but this would be some further research. Today we stick to I think we have 13 papers here that I presented to you. I hope you enjoyed it. I hope you had a little bit of fun of new AI research that was published today. Maybe you enjoyed, maybe you will have a look at the papers yourself, and it would be great to see you in my next video.